The last thing I'd like to talk to you about today is an application of systems of linear equations. Now, this is something we cover in our 116 class. We actually covered in our 096 classes near the end. The idea here is that you have a couple of unknowns that you need to solve for, and you've got at least a couple of conditions that give you some information, enough information, to where you can solve for the two unknowns. There are a ton of different applications where this situation pops up. The only thing that would make it rare would be if you say, well, yeah, but most times you have more than two things. Most of the time it's three things you're worried about, or it's four things you're worried about. Today I just want to restrict myself to talking about two things at a time. I'm going to show you one example, but you could apply that to anything. You've got kid 1 and kid 2, and you want to give them so much stuff. How much do I give each kid? Which, by the way, I advocate numbering your kids instead of naming them. It's much easier to remember. You just remember, the trauma kind of induces which one came first. Much easier to remember. Or name them all George, like Foreman did. By the way, this is off the topic, but the last time we had kids, we had a name picked out for a girl, and then we found out we were having two girls. So we liked the name Sarah. And then we found out we're having twins. I said, oh, that's easy. We'll just do Sarah sub 1 and Sarah sub 2. But for some reason, my wife didn't go, I don't know. She didn't like that system. So anyway, it would have worked for me. We're going to set up now the two conditions and the two variables will give us a system of linear things. Now, I'm assuming here we're not squaring things. We're not raising them to powers. We're just dealing with linear things. It gets a little more complicated if you start to square things. Okay? Here's an example. Adapt this to your everyday life, but I'm trying to do something very general, very everyday. A coffee shop owner wants to mix an expensive brand of coffee or expensive type of coffee at $9 a pound with a less expensive coffee to create a blend that will sell better. The expensive costs too much. The other one is considered not as good as the rest. So we're trying to mix a batch here, a 50-pound batch that is somewhere in the middle, okay? So there are two things that I need to figure out. How much of the expensive coffee, and I'll call that X. How much of the cheaper coffee, and I'll call that Y. And there's enough information here for me to solve for the two conditions. I worry about the weight. The sum of the two weights needs to be 50 pounds, so X plus Y is 50. The price, well, if I take $9 per pound on the one and $5 per pound on the other, I'd like to make that same amount of money by just simply charging $6.50 or 6.5 for each of the 50 pounds of the mixed variety. And you may want to multiply that out. I think it works out to 325 or something. So you've got two equations, you've got two unknowns. And we need to find X and Y that satisfy both at the same time. Now, this is where I need to talk theory with you just a little bit. There are three basic things that can happen when we look at two equations and two unknowns. These are linear things, so each one of the equations is going to give me a line, and it's possible that the two lines would be parallel. Okay? If you look at that, you can see that these are basically the same except for a sign, okay? But they are vastly different when it comes to this constant out here. Well, if those lines are parallel, you know what parallel means? It means they're not going to touch each other. And that means there's no point X and Y that satisfies both equations at the same time. So if that happens, you're not going to have a solution. Bad luck, try something else. The other thing that could happen that still, in a way it's the same case because you have parallel lines, but you have two lines that are identical to each other. Okay, you graph them both and they cover the same set of points. And you can see that here, that basically I have scaled, this bottom one is this one times a -2. -2 times that, -2 times that, -2 times that. Gives me the same line. Okay, now in this case you do have solutions, it's just you have a bunch of solutions. Every point on that line is a solution to the system. And that's not always helpful either. A lot of times you just want one solution. And that's case 3, where you have two lines, they're not parallel. If they're not parallel, they have to cross somewhere. Okay, and the two that I've drawn cross right there. Okay, that's your solution to the system. And in fact, that's a good way to actually solve these things numerically, is you can go into your calculator, graph the two lines, and then use your calculator functions to say, okay, what's the intersect of the two lines? That's okay, but that gives you numerical answers. So again, with answers like this, I'd have repeating decimals, okay, and that is actually the solution. I'd like to talk about methods for doing this symbolically. The one of two possible methods I can think of is what's called the substitution method. And this is where you find one variable in one equation, you solve for it, and then you jam that in the other equation. Okay? For example, in our coffee problem, and I've gone ahead and taken the liberty of graphing this just so you see that we are in this non-parallel case. There is a solution. It's right here. It looks like it's a little less than 20 for x and a little more than 30 for y. Okay. But I would solve for one of the two variables in one of the two equations, and because I don't want to generate fractions, I'm going to go ahead and just solve for y in the top one. So that would be 50 minus x for y. And then you take that and jam it into the y in the second equation. So here we go. You'll clean that up a bit. 9x and then a minus 5x will give you 4x. And then this is 250. Subtract that from both sides, you get 75. So 4x equals 75, divide through by the jump. X is 75 divided by 4, or if you convert that to a mixed number, 18 3/4 pounds. Then you back substitute. You've got a nice formula up here for x, so take this number, jam it in back up here, and you get y is 125 fourths, or if you prefer, 31 1/4 pounds. The sum of those is 50. And the value would be the same as if I charged 9 for what's there, 5 for what's with the other one. The other method that I can think of to do this, and a very common method, is to add multiples of the equations to each other. So in our coffee problem, what I would do is I would say, well, let's eliminate one of the two variables. I'll multiply by a -5 here, and that means I need to multiply by a -5 across the board. And then simply add them. The -5y and the 5y cancel each other out. I get 4x, I get 75. It's the same result. It's going to give me the same answer. That gives me the x that I found before, and you back substitute. You take this answer then, go back up here, solve for y, and you get the poundage for x and y. These are nice little methods, and I gave you that's kind of a rinky-dink problem. There's all kinds of different things I could think of. I don't have time to go into all the different types of problems where you have two things. Now, next week, I want to look at what if you have 3? What if you have 4? You know, what other methods can we use to solve these things? I've got some summary slides that will talk about the things that I talked about and kind of recap what we did.